I've been sent this pretty interesting algebra problem. And I think the question isn't properly formed, or it might be missing some piece of information. But it's an interesting question nonetheless, so I thought I would work it out, and we can talk about why it's not properly formed. So they give us a function, f of x. They say it's a third degree polynomial of the form ax to the third plus bx squared plus cx plus d. And they tell us a couple of the zeros of this polynomial. They say that we have zeros at the point -1, 0, and the point 2, 0. And they tell us that we have a y-intercept at the point 0, -2. And what they ask us is, what is a plus b plus c plus d? So let's see if we can make some headway on this. So the first thing is just think about is what would a third degree polynomial look like? And what are we even talking about when we say zeros? So let me just draw a little bit of a graph. And I don't know exactly what this third degree polynomial looks like just yet. Let me draw my axes. Now, a third degree polynomial can have as many as 3 zeros. And zeros are just the points where the function is equal to 0. So we have a 0 at -1, 0. So that's -1, 0. That's right there. We have a 0 at 2, 0. 1, 2, 0. So those are the two zeros that they've given us. They also told us the y-intercept at 0, -2. So it intersects the y-axis right there. But this guy could have as many as 3 zeros. Now, some of them might be complex. But complex zeros come in pairs of 2, the two complex conjugates. And I won't go into too much detail here. So this one must have a third real 0, because if the third one was complex, you'd need another complex 0. And you can't have 4 zeros for a third degree polynomial. So that third root, it could be sitting someplace out here, maybe over here, or it could even be a repeat of one of these two roots over here. But let's just assume that there's some third root. We don't know what it looks like. Let's say it looks something like, let's say that third root is sitting out here someplace. And then a potential graph, and I could be completely wrong, I'm just guessing, but just to get a sense of what third degree polynomials look like and how can a graph intersect the x-axis 3 times, a potential graph might look something like this. Curves and bam, hits the other 0, hits the y-intercept, and then goes back up like that. It might go like that. It might go the other way, go like that, up and then down like that. Well, there's many ways you could draw something that essentially curves twice to intersect these 3 points, and also that y-intercept. But I'm not going to go into all of those right now. But let's see if we can figure out the coefficients here. So the key point is me telling you that there must be a third 0 here. So let's call that third 0. It's at the point, let's call it R3, 0. And I'm using the letter R for roots. The roots are the x values of the zeros. So if we say f of -1 is equal to 0, we say that x is equal to -1 is a root. Similarly, we know that f of 2 is equal to 0. Or we could say that x equals 2 is a root. These are roots. So when someone tells you a 0, they're also essentially telling you the roots. And then we know there must be a third root at x is equal to R3. So x is equal to R3. Now, if we have a third degree polynomial where these 3 x values make it 0, we can rewrite this third degree polynomial as, I'll do it in a slightly different color, f of x is equal to x plus 1, and you'll see why I'm doing x plus 1 instead of x minus 1 in a second, x plus 1 times x minus 2 times x minus r3. And we want to put an a out front, and it'll tell you in a second why I'm putting this a out front. Because if you were to multiply just the x terms here, when you actually do your distributive property and multiply out these binomials, you'll just get an x to the third. But we had an ax to the third, so you're just needed a constant a there to make this an ax to the third. Now, why did I write it out like this? Well, if you put a -1 in here, what's going to happen? This term is going to be -1 plus 1. It's going to be 0. Who cares what these are or what a is? The whole thing's going to be 0. If we put x is equal to 2, This term right here is going to be 0. Who cares what the other terms or the a is? F of 2 is going to be 0. Similarly, when x is equal to R3, this last term is 0. Who cares about anything over here? So we know that this guy up here can be rewritten in this form over here. And so we're going to, if we can solve for R3, we can just multiply this thing out and try to do a little bit of pattern matching to figure out what these coefficients are going to be. Now, the other big clue they gave us is the y-intercept. That point right there, the point 0, minus 2. They're telling us that f of 0 is equal to minus 2. Well, what's f of 0? F of 0, I'll write it here, f of 0. If you put 0 in here, this term becomes 0. This term becomes 0. That term becomes 0. You're just left with the d. So f of 0 is equal to d, or we could say that d must be equal to minus 2. D is equal to minus 2. So we solved at least one of the coefficients, the constant term. D is equal to minus 2. Now, if d is equal to minus 2, that means all of these constant terms, when you were to multiply out this expression, and I would include the a, because the a is scaling everything, then that must be equal to minus 2. Let me be clear here. So let me rewrite this expression. This is equal to, I'll just multiply the a times this last term. We can do it in any order we want. So this is the same thing as x plus 1 times x minus 2 times ax minus let me write, minus a r3. This is the exact same thing as this thing up here. I'll just write this is what f of x is equal to. And this is the exact same thing as that up there. Now, to solve for an R3, or attempt to solve for an R3, you just have to realize that when you multiply this thing out, the way to get the constant term over here, or the d over here, is that's going to be a product of the constant terms in our expressions. Because if I introduce any products with any x terms, you're going to get one of these other terms over here. The ax cubed term is generated from that term, and that term being multiplied together. And then the constant term is multiplied by the constant terms being multiplied together. And then these two in the middle are multiplied by different combinations of constants and x terms. And you'll see that when you if you actually want to multiply this out. But if you take my word for it, that times that times that times, actually, let me write it this way. That times that times that have got to be equal to d, we can then attempt to find some relationship between a and d, which is minus 2. So we could say 1 times minus 2 times minus ar3, these two minuses will cancel out, is going to be equal to our d term. It's going to be equal to minus 2. And so if we simplify that a little bit, we get 2ar3 is equal to minus 2. Divide both sides by 2a, and you get r3 is equal to minus 1 over a. So we haven't solved for the third root. We've just gotten it in terms of our coefficient a. But let's see if we can still use that in some useful way. So if r3 is minus 1 over a, this term right here becomes what? Let me rewrite it. All right, I'll do it in blue. F of x is going to be equal to x plus 1 times x minus 2 times ax. Now, minus a times r3. Let me do it here. Minus a times r3 is minus 1 over a. So that's a minus times a minus. That's plus. The a's cancel out. You just get a 1. So this term now, if we substitute r3 with that, this will just turn into a plus 1. Minus a times minus 1 over a. That's plus 1. Plus 1. We just substituted that for that to get this right here. Now let's multiply this thing out. Let's actually do the algebraic multiplication and see what we get. So first I'm going to multiply these two terms. Let me do it in a different color. Let me multiply those two terms right there. So this is going to be equal to x squared plus 1x minus 2x. So that's minus x, right? 1 times x is x. Minus 2 times x is x minus 2x. So it's minus x. And then minus 2. Just multiplied these two binomials out right there. And then I'm going to have to multiply that times ax plus 1. So I'm going to write the ax plus 1 down here just to save space. Ax plus 1. And now we just do a little bit of algebraic multiplication. 1 times minus 2 is, I'll do it in magenta, minus 2. 1 times minus x is minus x. 1 times x squared is x squared. Now, ax times minus 2 is minus 2ax. Minus 2ax. Ax times minus x is minus ax squared, right? Minus ax squared. And then ax times x squared is ax to the third. Ax to the third. And then we add everything together. And we get our f of x is going to be equal to ax to the third. Let me scroll to the left a little bit. Ax to the third. X squared minus ax squared. So that's plus 1 minus a, 1 minus a, x squared. And then we have these two added together. So this is minus 1 minus 2a. Or we could say that this is, we could call this is equal to, so minus 1 minus 2a, this is, or we could say minus 1 plus 2a x. And then we have our minus 2, which makes sense because that is our d. That's our d. So this is really the solution. This is the form that our equation is going to take. And the reason why I said in the beginning of the problem that the equation or the problem wasn't well defined is that I can pick any arbitrary, I could pick any really real number a, and this equation will satisfy these conditions that we were given. So I suspect that I wasn't given all of the constraints on this problem. Maybe there was a third constraint, that a is equal to 1, or b is equal to something else, or a plus b is equal to something else. But just using these constraints, the equation will take this form. So if it was in this form, of course, this is a, this is b, which would be 1 minus a. That's b, that's a. And then this right here is equal to c. So we could pick, if we could pick one particular choice if we just want to get an answer to their problem, but it might not be the answer they were looking for because they might have picked a different a. But if you just pick a simple a is equal to 1, then what's b equal to? Then b is equal to 1 minus a, which is equal to 0. Then b is equal to 0. And then c is equal to, actually c would be include this minus sign right there. C would be 1 plus 2a. So 2a is 2. 1 plus 2 is 3. Put a minus sign. So c would be equal to minus 3. And of course, no matter what we do, d is going to be equal to, d is equal to minus 2. So if we put a is equal to 1, the answer here to what is a plus b plus c plus d would be equal to 1 plus minus 3. 1 plus minus 3 is minus 2. Minus another minus 2 is minus 4. That's one possibility. But we just as easily could have picked, a could have been something, it could be a fraction. It could be anything. It could be, a could be minus 1. A could be equal to minus 1. If a is equal to minus 1, then b is equal to 2. Then b is equal to 2, right? 1 minus minus 1. And then c is equal to 1 minus 2, which is minus 1. But then you have a minus out front. So then c is equal to 1. And then d is always going to be equal to minus 2. D is equal to minus 2. And then you have a plus b plus c plus d would be equal to, well, these would cancel out. You would get them equal to 0. So we don't know exactly what answer the problem writer was looking for, but this is a pretty interesting problem. And then, just out of curiosity, if, let's take this first example that we took, where a is equal to 1, we could then look at what our root must be. If a is equal to 1, then our third root is, then r3 would be equal, that's just for this situation, let me write here, then r3 would be equal to negative 1 divided by 1 would be equal to minus 1, which means that we have a repeated root. We would have a repeated root right there, that we wouldn't necessarily have a distinct root out there. And if we're curious about what that would look like, let's look at the situation where a is equal to 1. Actually, maybe we look at both of them. When a is equal to 1, our equation is x to the third. Where's the x button? X to the third there's no x squared term, minus 3x, minus 3x, minus 3x, minus 2. So that's, let's graph both of them simultaneously. So that's this one, where we pick this choice of coefficients. And then let's do this choice of coefficients. So if we have minus x to the third, right? A is minus 1, plus 2x squared. And then we have plus x, c is 1, plus x minus 2. So those are our two graphs. Let's see what they look like. Let's graph them. So our first one, there we go. We hit that point. That's our double root. Notice, both of these two graphs meet our two constraints. They both have a root there at minus 1. They both have a y-intercept at y is equal to minus 2. And they both have a root at x is equal to positive 2 right there. Now, the second one right here had a separate, distinct third root, while this first one here has a double root right over there. But anyway, I actually think this problem was somewhat more interesting by the fact, we had to actually look at the different solutions to it. And there's actually an infinite number of solutions to this based on what you choose for your A.